Okay, we have Mathieu Tanneau here presenting what was going to be his talk from the 2019-2020 JuMP-dev workshop. It is now online, so Mathieu, please take it away.
Thanks, Maris. Hi, everyone. So just before I start, all the talk material is available online in that GitHub repo that's JuMP-dev 2020. And for those who are interested, there's also a technical report online at the archive URL. And before I start talking, I just want to advertise that I'll be defending on October 2nd. I'll be talking about using decomposition methods within power systems, a bit about structured report methods, and some work that I've been doing on disjunctive cuts in mixed integer conic optimization. So there should be details at the website of our research group, whose URL should be on your screen. So if you're interested, just stay tuned, and there should be a public invitation in the next few weeks. All right, so today, what I want to talk about is first the motivation behind Tulip.jl, so how it came to be. And then more specifically, I'll talk about some design choices that I made in the code to allow the use of specialized linear algebra. And then I'll finish with some lessons learned about internal data structures when you're writing an optimization solver. At any point, don't hesitate to ask questions or interrupt me, because I think the overall presentation is actually going to be fairly short. So let's start with the motivation. We're looking here at linear programming problems. So there are optimization problems that have linear objectives, linear constraints, and all variables are continuous. You can write them in different forms. One of them is called the standard form, which is the one presented here, where you only have equality constraints and non-negative variables. You can always reformulate any linear programming problem into that form. So it's fairly generic. And once you have that, typically you can solve it with either the simplex method or an interior point method. And today I'm going to focus on interior point algorithms. This will be all the math that I will be talking about today. Basically, all you need to know about interior point algorithms is that a big computational part of them are solving linear systems, specifically augmented systems of this form. So you have a symmetric indefinite matrix, which is a 2x2 block matrix that involves the constraints matrix A transpose, and then some diagonal scaling matrix, theta inverse. And you will solve that for some right-hand sides. It can be reduced to a system that's called the normal equation systems, where essentially you pivot the theta block, and then you get a positive definite system that is also symmetric. In Tulip, actually, what is solved is a regularized version of that system, which basically has a diagonal perturbation. It's basically changing the diagonal of the matrix so that the system is better conditioned and numerics work better. There's a mathematical justification behind it. You can look it up in the paper, but I won't be talking about that too much. The important features of that regularized matrix is that it's still symmetric, but now it's quasi-definite. And symmetric quasi-definite matrices are amenable to LDL transpose type factorizations. So you can essentially take this matrix, put it into LDL, and then you get a factorization and you can solve the linear system. Whereas if you're doing that with this matrix, it would fail numerically, and you get something like a quasi-definite error. So numerically, the system is a bit nicer to work with. And the whole design of Tulip is to write a code that allows you to exploit some structure in the matrix A. And the goal of doing that is to speed up the resolution of the linear systems. So you can do that through more efficient data structures, some specialized matrix vector products, and some specialized factorization routines. And of course, we want the code to be flexible enough so that if you want to change that particular component of the code, then you don't have to change the rest of the code. When I started to work on this project, I knew I wanted to do interior points, and I knew I had to change the linear algebra. And After a few weeks of looking at open source solvers, I realized that it was actually going to be faster for me to write an interior point solver from scratch than actually change the linear algebra components of, say, GLPK or CLP. So hopefully, if tomorrow you want to do some of the things that I present here, you won't have to rewrite everything from scratch. In practice, there are 3 requirements for you to do that. The first one, which is actually the easy part, is you know about the structure. Now you need to develop the right data structures and algorithms to exploit that. So you need to define your own data structure, some efficient matrix vector product, and then some efficient factorization routine. That is only a few hundred lines of code, no more than that. And it's actually pretty straightforward if you know your problem structure. The harder part is to integrate them within the IPM algorithmic framework, meaning you have an interior point algorithm, now you need to plug in the specialized factorization and then specialized data structures. That's a bit trickier, but that is essentially the main point that Tulip makes easier. And the last part, which is more of a discussion really, is how to convey structure information to a solver. Right? If you're modeling your problem with JuMP, there should be a way for you to say to the solver, hey, you know what? This is the structure of our matrix, without you having to make too many going around just to make it work. So that's the 2 points I'm going to focus on today are points 2 and points 3. But the third one is, to me, still kind of an open question. So if anybody has comments on that, I'll be very interested to talk about this afterwards. All right, so just before I get into the details, I'll show you some examples of what you can do with Tulip and what the user-facing part looks like. So something you can do is to solve a problem in different arithmetic. And specifically, that is going to be chosen when you instantiate the model. So for instance, you can solve a problem in double floating point arithmetic. And you prescribe that by choosing float 64 when you create a model. And then just load the problem, optimize it, and the objective value is going to look something like that. In some situations, you might want a higher precision solution. And you can do that by just setting the arithmetic to say quadruple precision. And the rest of the code is exactly the same. It will load the problem, run the optimizer, and then when you create the solution, you will have something that is in quadruple precision, meaning that the numerical tolerances are also going to be much tighter. So double floating point precision typically gives you 10 to the minus 8. Quad precision will give you 10 to the minus 60. Of course, it's much slower to do quad precision than double precision. But if for some reason you have this one problem where you really want a very accurate solution, that's something you can do. And it's going to be essentially convenient to do that within the existing framework of Tulip. If you use quad precision, you should expect something like 1 order of magnitude slower execution, just because float 64 employs hardware acceleration, while float 128 does not. There's a double 64 numerical type that allows to be a bit faster. But overall, you should expect your code to run something like 10 times slower than the default. Another use case is when you're developing some code where you have to solve some LPs, and for some reason that code is not working. Now, there may be different reasons to that. It might be that you have a bug in your code. It might be that your problem is numerically bad conditioned. It might be that your algorithm is incorrect. So one thing you can do to help in the debugging process is solve all the LPs in extended precision. And that way you can essentially remove and isolate the numerical component. And that can be useful when building some new optimization tools. That's a feature that's also available in MathOpt interface by just templating the optimizer call. So you can do Tulip.optimizer of float64, and that will give you double precision. You can do Tulip.optimizer float 158, and you get quad precision. And of course, you can do big float and others. Now, the feature that I'm going to talk about a bit more today is how to use specialized linear algebra. And specifically, there are parameters that you can access that allow you to specify which data structure you want to use for storing the constraint matrix and which linear solver you want to use for solving linear system. And these options allow you to choose, for instance, between solving the augmented system or the normal equations, whether you want to use a direct or indirect method, which backend you want to use. So by backend, I mean which essentially linear algebra library. So are you going to use toSparse, mumps, Paradiso, and so on. Once these options are given by the user, multiple dispatch is going to take care of the rest. So there's no real change to the underlying code. Everything is handled by the compiler. So for instance, if you want to use dense linear algebra, you set the matrix option to say, I want to store my matrix as a dense matrix. And I want to use a dense linear solver, which is going to be here. So this dense symmetric positive definite solver. And some information about the linear solver that you're using is going to be displayed in the solver log. So for the two options above here, the log is going to show you that you're using float64 arithmetic, that you're using NetBack as a backend, and that you're solving the normal equation system. And of course, these are customized based on the solver that you're choosing. So in practice, switching between linear solvers is as easy as the following. This is how you would solve the normal equations with the ChOL-mod module in toSparse. So you just say that I want to use a ChOL-mod solver and I want to solve the normal equations. If you wanted to solve the augmented system, this time with a package that's called LDL factorizations, you just say that you want to use the LDL factorization for symmetric quasi-definite matrices, and that's what it will solve. If you wanted to use an indirect method, like a Krylov method, so that's a PR that's in progress, but soon it should be merged. So you just say that you want to use the Krylov positive definite solver and, for instance, the MinRes method. And so just setting these parameters will then select the right linear solver and implementation that you want. So these are, let's say, default supported solvers that are existing in the code and that you can use without having any additional dependency. You can also use custom routines. So for instance, I coded a small unregistered package that's called unit block angular that defines a custom data structure that's called a unit block angular matrix and a custom linear solver that's called unit block angular factor. And in that, I have coded specialized matrix vector and factorization routines. So that's one of the examples that is given in the paper, if you want more background on that. And then this is how you would be using it when solving a problem. So after you've loaded the problem, the match for setting the matrix, so we set the matrix option parameter to using the unit block angular matrix with, here there are some specific parameters. So this is saying that there are 24 linking constraints, 72 linking variables, 6,421 columns, and 124 blocks. Everything that is on the second line are essentially keyword arguments that are going to be passed to the constructor of the matrix. So that allows you to really customize everything you want. And then once we've said that, we just have to say that we want to use the unit block angular factor linear solver. And that's it. If you're using default linear algebra versus specialized linear algebra, essentially you get pretty much the same thing, but it's much faster. So on a baby example, I could solve in about half a second with ChOL-mod, which is the default setting. And if I were using my specialized code, I would solve it in about a third of the time. The whole unit block angular package is 265 lines of code. including doctrines. And just by doing that, you can get up to 10 times faster on problems that have that particular structure. So it's you can get very good improvements for a very cheap cost in terms of how much code you need to write. And
quick question.
Yeah.
What does unit mean in the block angler? I know what block angler is. What does unit mean?
So it means that all the diagonal blocks are unit blocks.
Okay.
It's a special type of block angular matrices. And detailed knowledge of that is not very important for understanding what I'm talking about today.
Yeah.
So that's why I'm not giving too many details. But in the paper, you'll have all the formulations and the correct definitions.
Okay, thanks.
Yeah, so in the end, what I want to stress is that if I were able to come back something like 2.5 years ago and do the work that I had done at the time, today it would only take me about 250 lines of code to get a specialized solver for the problems that I'm considering. And that was a big improvement over the about 2 years that it took me to get the solver to speed to where it's now. So now I'm going to talk a bit more about the implementation. Just so you get an idea, Tulip is about a little bit above 4,000 lines of code. So all these numbers include docstrings, so it's actually a bit less than that. And it's decomposed as follows. So you have about 600 lines of code for core data structures. So something like how to solve an LP problem, how to get a solution, and so on. The pre-solve module is about 1,000 lines, so it's actually pretty big. The KKT module, which is where everything about linear solvers is handled, is about 600 lines of code, so it's also very small. The IPM algorithm itself is only 750 lines, which you could probably make a bit more compact, but I decided to have a few layers so I can extend it afterwards. And finally, one of the larger modules is everything that has the interfaces, so including the math-out interface wrapper. If you sum that and you had a few modules that I didn't put in there, you get roughly to 4,000 lines. So compared to that, writing a specialized linear algebra, it's only about 5% in terms of line of code of the solver itself. And in terms of time, it's about, it's roughly proportional. So coding the specialized routines I showed before took me about 3 weeks, starting from a point where I didn't know, I had zero knowledge of Julia. So even if you don't know the language, it can take you only a few weeks to write some specialized routines for a specific structure that you know about your problem. When you get there, which is like step 0 of your research project, all the rest, so integrating that into an integer point solver, getting it to be usable by the user, it's 95% of the work. And I hope that I've done a sufficiently good job so that that 95% part doesn't have to be repeated now. So that's kind of my hope with this package. So how do we do it in practice? The first part is that there are several representations of the same problem. So there's an LP that is the one that users interact with, which is stored in a very generic form. So you have linear constraints with upper and lower bounds, continuous variables with upper and lower bounds. All the upper and lower bounds can be finite or infinite, and then you have an objective and an objective constant. The second representation is a pre-solved problem. It's in the same form as a user-facing, it just has less rows and columns because those were removed during pre-solve. And finally, the form that is passed to the optimizer is a standard form LP. So this one, meaning that we go from the original form to the standard form by writing everything in terms of equality constraints and non-negative variables with potentially finite upper bounds. Internally, this is how things are going to look like. Once the user has given the model and has called optimize, there are a number of steps that are performed. First, we perform pre-solve, and then we extract a reduced problem. So it's a smaller problem after a number of reductions. The third part is we convert the reduced problem to standard form. Once we've done that, that's where the constraint matrix is actually instantiated. So that's where this matrix option parameter comes into play. Afterwards, we instantiate a KKT solver, so for solving the linear system, and only then do we start optimizing. And once we've done with optimizing, there's a post-solve step, which essentially takes a solution of the reduced problem and extracts a solution to the original problem that can be returned to the user. So there are a few steps to be done, and each of them comes with its own design principles and constraints and philosophy. So the matrix instantiation is coded in the following. There's a method that is called construct matrix that is going to be called from within the solver as follows. So it calls construct matrix with the type of the matrix, number of rows, number of columns, so number of constraints, number of variables, and then the constraint matrix in COO format. So row index, row indices, column indices, and then coefficients. And you can also pass some keyword arguments. So for instance, if you wanted to instantiate a sparse matrix, then you're just calling the sparse method. But this is a method that users have to extend if they want to write the custom matrix types. Now, for instance, if you call construct matrix with a sparse matrix CSC, then it's going to return you a matrix A in sparse format. So I convert it to matrix so that it displays a bit nicer. So the first row, which is here, has only one coefficient of 1.1 that corresponds to the first column. So that's this one. There's one column that is empty. It doesn't show up anywhere. And then the second row has coefficients 2.2 and 2.3, corresponding to columns 2 and column 3. So that, that's about all that there is for instantiating matrices. It's not very complex. Basically, everything is done by this method, construct matrix. And the fact that I provide the type of the matrix allows for multiple dispatch type of specialization. So as soon as you give a specific type, then you can extend construct matrix with this signature, add some keyword arguments if you want to, and that will be called automatically. The only limitation right now is that it's going to be called for the standard form, not the original form. So that's one thing that I have to improve on in the future. The next part is linear systems. So within each interior point iteration, you have one factorization that is typically expensive, a few triangular solves that are going to take a non-trivial proportion of the time, but probably not as much as a factorization, several matrix vector products, and then many vector operations. So the fact that the factorization is reused for several solves within the same iteration makes it, in a sense, logical to have some persistent data structures so that you can reuse the storage, you can reuse the factorization, and that also allows you to do some dispatch internally. So that's the option that I went with. Now, specifically, there's an abstract type that's called abstract KKT solver, and then there are three functions that, once again, if you want to implement your own customized solver, then these are the things that you need to extend. The setup function is going to be called once, and it's essentially instantiate the solver. So that's where you would do symbolic analysis, memory allocations, things like this. Then every iteration, Tulip is going to call this kkt.update function, typically to update the factorization. And then within the iteration, every time a linear system is to be solved, it's going to be called, Tulip is going to call this kkt.solve function. And then since you have this kkt argument, which is not simply the linear solver object, then you can extend that and do dispatch on that for efficiency. And finally, the kkt solvers, or specifically which one you want, is going to be chosen via the kkt option parameter. So for instance, you can say that you want the Krylov positive definite solver and that you're going to be using the Krylov.minres function for doing that. The setup is done, like I said, after pre-solve and after matrix institution. It's called as the following. So this is the function as it gets called within the interior point algorithm. So we call setup, and we're given the type of solver, the matrix, and then some keyword arguments. If there's no specialized dispatch that was given by the user, this call will default to the following. So it's just calling the constructor of the linear solver on the matrix A, and then whatever keyword arguments were given. So it's basically, it behaves like a factory, essentially, or at least this is how I see it in my mind. And if you want to implement your own solver, then you need to implement a version of your constructor that will take as argument the matrix with potentially some dispatch on the type of the matrix and then some keyword arguments. The update, which is called once per iteration, has one and an only role. It means that after you call update, you can use the kkt solver to solve the augmented system. And the values of the primordial regularizations are controlled by the algorithm. So that's why they're passed as arguments. So if you're using a direct method, so something like a Cholesky factorization, that's where you're updating the factorization. If you're using an iterative method, there's no factorization to update, but you might have a preconditioner, for instance, that might be updated at this point. And that's about it. So this kkt.update call can be as simple as just updating an internal storage and then calling a factorization method. And then finally, the solve function is pretty self-explanatory. You're basically solving the augmented system. And that's it. Any questions so far? Nope. Okay, I'm going to continue. I mean, I know everyone is muted. So if you want to ask a question, you can either unmute yourself or ask it in the chat, and I'll be notified.
Mathieu, can you hear me?
Yes.
Yeah, just in case, so the fact that you have this construct matrix function, it was just to have a uniform interface for constructors of types of constructors of matrices, right?
Yeah, so it also has to do with how we handle the, let's say, the model representation. So this problem, I have my Tulip has its own data structure that currently you cannot touch. I need to store the matrix in a form that I'm going to detail in a short bit. But when you're given that, when you're giving that to the optimizer, you might want to use a different data structure for storing the matrix. And that's where the conversion comes in. So the reason for having this construct matrix is to allow for some customization level when transforming from this form to this form. And you might have a very efficient matrix form, a very efficient data structure for, say, computing matrix vector products, but that would make it extremely slow to iteratively add columns or constraints or change coefficients. So all the data structures here are made to simplify access and modification, but they're not meant to be fast for linear algebra. And all the methods here and data structures are meant for fast linear algebra, but potentially slow access and modification. And the construct matrix that is here essentially does the conversion between the two. It's probably not a perfect way of doing that, but it's the one that I came up with. And so far it works for the needs that I have. But if anybody has better suggestions, of course, I'm very happy to hear about it.
It makes sense, thanks.
Okay, so since we're talking about data structures, here are some of the things that I learned kind of the hard way when I was coding to it. So the first part is, interfacing with the user. Users never work with a standard form formulation. You never have a problem that only has equality constraints and non-negative variables. You're going to have some range constraints, some greater than or equal to constraints, some lesser than, some variables that have a lower bound of -1, and you have to take that as input and convert that to standard form. Or you can use some bridges in Math interface to do the reformulation for you. So I decided to allow some fairly more general interface so that I could customize a few things myself. But in spirit, it's very similar to the goal of matrix opt interface, which is to allow essentially users to formulate models and then get a matrix representation. Now, where we're talking with users, meaning when users are creating, modifying, accessing things with the model, we need data structures that are constructed as follows. It needs to be efficient to add or remove columns, constraints, or individual coefficients. So that's one of the requirements. You need access to individual coefficients. It's a bit more rare, but it should still be a possibility. You need to ensure that the indices of the rows and of the columns remain consistent. Meaning when you remove the first variable, then all the variables should be shifted by -1. And when you remove a variable that's in the middle of your problem, then you need to ensure that everything that's afterwards remains consistent. So that's also something that needs to be addressed during development, and that is more or less easy depending on the data structure that you have. And finally, for pre-solve, the most important feature is you need fast access to row-based and column-based iteration over A. Meaning pre-solve essentially goes through constraints and columns of the matrix and then perform some small reductions. So for that, you need to go through the matrix several times. You need to do it fast, and you need access to rows and columns. So initially, I thought, well, why do I need fancy data structures? Let's just put everything in the dictionary. Store coefficients based on the value of the coefficients based on the index, and that's going to be way more convenient. It's very slow. It's actually not that convenient at all. Especially if you start deleting coefficients or variables, then getting everything consistent can be a big pain when we're just using dictionaries. So the current implementation is similar in principle to what Soplex is doing, meaning that I store 2 copies of the matrix and I ensure that they remain in sync. The first copy is a column-based copy, so it's essentially a vector of column. And the second copy is a row-based data structure, so it's a vector of rows. And now if you want to go row by row, then you just access the A through A rows. If you want to go column by column, you just access it through A calls. It's redundant, so it uses twice the memory that you would need, but it's way simpler for accessing things and making things efficient. Of course, there's a bit of accounting there, because every time you add or you make a modification, you need to account for it in both copies of the matrix. And then each individual row or column is actually just a sparse vector with stored in the indexes so that modifications are a bit easier. So the internal structure is exactly what you would see in a sparse vector, except the length of the vector is not specified. So we just stored the non-zero indices and the non-zero values. And these are the elements that get modified whenever we delete a variable, we add a coefficient, or we modify one. What remains slow is deleting columns or rows, because every time you do that, essentially you have to shift all the metrics. So if you're deleting a variable, updating this is going to be very fast. Updating this one is going to be very slow. And if you delete a row, updating the row is going to be fast. Updating the columns is going to be slow. To be honest, I don't think there's a silver bullet here. It probably depends on the use case. But in some of the experiments that I did, I needed fast modifications, so adding columns very fast. So that kind of data structures so far has answered my needs. But there are obvious improvements. Yes, Julia has linked list. So there's a question, does Julia have linked list? They do. I saw a few implementations. I'm not sure on the top of my head that they're incorporated either in the standard or base library. And it might solve the issue for updating. But then the pre-solve part might remain. And I think so from one of the solvers that I looked at, they were using double linked list. So JLPK, for instance, has a double linked list storage where each element in the list, we have a pointer to its follower, to the previous element. And in JLPK, they also have pointers to the previous rows and subsequent rows. So there's a bit of work to be done here. But to be honest, it's not a bottleneck as of now. So until someone has a use case where really problem modification is a huge bottleneck, that's not going to be the priority for development, at least for me. But there's obviously some room for improvement. Speaking of which, some improvement opportunities currently would improve batch modifications. So if you want to say add 5 variables or delete a bunch of variables at a time, currently this will default to individual calls, which is not as efficient. I recently discovered that there's a package that's curated by the people that are behind Coluna that's called dynamic sparse arrays. It might also provide some useful data structures here. And one area that I might explore is to enable user customization of these data structures themselves. So not store by default the matrix in columns and row based, but allow the user to have a customized data structure here. The use case I'm thinking particularly are distributed models, when you want to have a matrix that is distributed over potentially several machines, and then to have operator-based modeling. So where you don't know the matrix itself, you just have a linear operator over that. And this might not fall well under the current paradigm. Of course, the limitation is that anything you would change here is going to interfere with pre-solve, because the way I currently have pre-solve is integrated to that data structure. So there's like it's a bit of extra work to change these things. But once again, creating a model, modifying a model, and running pre-solve is not what takes most time right now. So it's not a performance issue. It would be more of a feature issue if someone say really wanted to have distributed models. Then we would have to make some modifications. Okay, so I'm about done. I'll just outline a few of the future directions that I'm considering right now. I'm not going to talk about math of integer points, so I'm just going to highlight some directions that directly relate to implementation and the package itself. So the first one would be to support quadratic programming. So their optimization problems with quadratic objective and union constraints. The algorithm is exactly the same, except that the augmented systems have this Q matrix in addition to the diagonal scaling theta inverse. But it should be a relatively minor update of the code, relatively with some caveats, of course. So that's one area. The other one, which I'm currently working on, is to have iterative linear solvers to be implemented. So there's a PR that's in progress that will introduce some initial infrastructure for doing that. The package I'm using here is Tulip.jl. They have a number of Krylov methods, such as conjugate gradient, conjugate residual, minres, and a bunch of others. And I happen to know some of the developers of that package. So far, we're just introducing some, let's say, data structures and infrastructure just to check whether that's feasible or not. But to actually be able to use that in practice, we'll take some changes to the three-point method to address both speed and numerical issues. Another thing would be to have specialized solvers for wider classes of problems. So one I'm thinking about are block angular problems that arise, for instance, in large-scale stochastic LPs, and have those integrated with modeling extensions to JuMP, such as struct JuMP or block decomposition. So the idea here is that the user can identify a block structure in the problem, and then this block structure can be passed directly to specialized solver within Tulip. And then that would hopefully speed up the resolution. And one opportunity for this is parallelism, of course. Speaking of parallelism, eventually, I hope that I'll be able to have GPU support. Most likely, this will come as part of a specialized linear solver first, and then maybe at some point a more wider support. And that's it. Okay, so there's a question about whether Tulip addresses the one discussion that is going on in Tulip. I've actually answered a few times on this thread, and I think it answers the question, do we have a native Julia LP solver? And I want to say that the answer to that is yes. But the discourse topic has grown way beyond that, and I don't want to get the discussion that wide at this point. The second question from Mathieu is whether QCQP would work with a roughly similar system. If I'm not mistaken, QCQP would give you additional terms in the lower right term here. It's slightly more involved, especially if you have a homogeneous form as we have in Tulip. So it might require some heavier modification, yes. And then the last question is about GPU support. So there are two ways that we could use GPUs. The first one would be to use it just for matrix vector product. So once we have iterative methods, we can essentially store the matrix on a GPU and then run all the methods of Krylov that are compatible with GPUs. We can run them on a GPU directly. This would require a minimal modification of the code. And essentially, it hides all the complexity and makes it fall on the linear solver. Having let's say a general GPU support, that will require some heavier refactorization. I have not tried to use Tulip with Julia's generic AD tools. It might be something for the future, but I'm not personally involved in that. I have no knowledge of that. I mean, I have zero experience essentially with AD and Zcot. So unless someone wants to use it or I end up working with it, it's not on my to-do list at the time. Then there's another question on how to use a good preconditioner for iterative methods. It's currently an open question, but some of the people who are working on Tulip.jl, so these are the people who are experts in iterative methods. They've been working on solving if-condition systems, and they're the ones who will have the answer to that. But at this point, it's still an open question. And then Miles asked a question about higher precision. So just to give back some context, when I was saying that I can use high precision, I mean every single operation is going to use high precision. And obviously it's very expensive. And so Miles is suggesting to use higher precision more strategically. So it's obviously something that could be done. The easy part would be to first solve in, say, double precision up to some tolerance, then switch to higher precision and do a few iterations. The reason I have not done that so far is because it would require some change to the algorithm. And the convenience of the current way it works is that I didn't have to change anything. So I essentially got the high precision for free at the cost of performance. But there are a number of strategies, yes, that could be explored to address this part. And one of them would be to use mixed precision. So lower precision and then increase precision as things go, or when we detect numerical trouble. Did I manage to answer most of the questions?
Yeah, I think you managed a lot of questions. So let's wrap this up. Thanks a lot, Mathieu, and we'll take any more questions offline.
Thanks.